This must be team 3. 1, 2. So team 2, you got 11 out of 12? Yeah. Okay. Wait, you're team 1, right? Oh, okay. They're team 2. We're good. Teams 1 and 2, awesome job. You guys did really well on this. Okay, before we start this unit, tell me, in Algebra 2, you guys did learn exponential and logarithmic functions, right? How well do you remember logs and exponential functions? Kind of, sort of, but it's in there somewhere? Okay, so these are just some equations. I'm hoping that you guys have had exposure to these before. These are just definitions. Exponential population model. You guys have done stuff with population? Like when populations increase? Maybe? Maybe not? It's okay if you haven't. Alright, if a population P is changing at a constant percentage rate R each year, then this equation applies, where P naught is the initial population, R is expressed as a decimal, and T is time in years. Sorry that it's kind of smudged. The copy machine has been giving us trouble the last few days. A logistic population model. Exponential growth is unrestricted, but population growth often is not. For many populations, the growth begins exponentially, but eventually slows and approaches limited growth. This is actually a definition that appeared in our last packet also. Do you guys remember? But we didn't do, I think we had like one problem with it. There were a few problems in your homework also. We'll do a little bit more with it this unit. So, the logistic growth function is one of these, depending on what you're using. The A, B, C, and K are constants. B is greater than 1. C is the limit to growth. If B is greater than 1 or K is less than 0, these formulas yield logistic decay functions. Unless otherwise stated, all logistic functions in this text will be logistic growth functions. Logistic models are another topic that may or may not appear on the exam. If it does, I do want you guys to have some exposure to it. The big difference between an exponential function and a logistic function is that an exponential function continues growing at a really strong rate the whole time, whereas a logistic function eventually tapers off as it approaches some limit. So population models usually follow logistic functions because population doesn't typically continue to grow exponentially forever. Usually at some point it starts to level out when it hits the whatever maximum population is comfortable for that particular area. Alright, let's do some examples. Example number 1. Suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 350,000. All right, let me see if I can. Okay, our initial amount of bacteria is 100, and if it's doubling, that means it is increasing 100%. Right? It's increasing 100% every hour. 100% written as a decimal is 1. So here's the equation we're using. I'm going to plug everything in. So the equation we have is 100 times 2t. And we want to know what t is at what time. This is going to equal 350,000. So in my calculator, I'm going to plug in 100 times 2 raised to the x power, and then 350,000. And I'm going to change my window. Let's see here. We're really only dealing with positive numbers of hours, so let's do 0 to 20 for x. For the y's, it needs to go at least to 350,000. So let's do 0 to 500,000 with a scale of 10,000. Let's see what that looks like and we can play with it if it doesn't look good. So there's my exponential function, and there's my constant function. Second calc intersect. First curve enter, second curve enter, guess enter. It looks like it intersects at 11.773 hours. Yes. Oh, so I knew that my y value had to include 350,000. So I just made the max 500,000. But I didn't want to have 500,000 dashes, so I made the scale 10,000. For the x-min and x-max, I knew the time had to be positive, so I made my x-min and y-min 0. For x-max, initially I put 10, but then I thought it might be a little bit past 10, so I put 20 just to see. And it turned out to be a good estimate. If I had done this initially, like I was thinking of doing, what I would have seen is, oh, it's intersecting somewhere over here. And then I would just need to change my x max to something that included that. Are you guys becoming more comfortable playing with your window on the calculator? Okay. Do you guys feel like you could solve one like this? Maybe. All right. Practice number 1. Determine the exponential function with initial mass 0.6 grams, doubling every 3 days. Let's do this. Just give me the equation. Don't give me the answer yet, just give me the equation. Give me the exponential function. Yes, good job. What's R though? You guys let's? You know what? I just realized this problem actually isn't asking you to find the point of intersection. I thought it was. My mistake. All they want is the equation. Get it? I thought there was a part B, but I guess not. What's R? Okay. Here is the answer, ladies. So R, once again, is 1 because it's doubling, which means it's increasing 100% each time. And then we'd have to divide this by 3 because it's doubling every 3 days, not every day. Great job, everyone. And so here is the function. Many of you gave it to me like this, which is also fine. All right, does anyone need more time on this page? Okay. All right, I'm now turning the page. Yell at me if you need more time. Okay, example number 2. Suppose the half-life of a certain radioactive substance is 20 days and its mass is 5 grams initially. Find the time where there will be 1 gram of the substance remaining. Okay, so to start, our initial amount is 5 grams, and in this case, the rate is negative 50%. Does it make sense why it's negative? No, because it's a half-life. That means every 20 days it's cutting in half. And then after another 20 days, it's going to cut in half again. So whatever value we have, we're subtracting 50% of that. Written as a decimal, that's negative 0.5. So plugging everything in, we've got 5 times 1 minus 0.5 raised to the t over 20 power. I'm putting all my t's kind of in cursive just so they don't look like plus signs. So this becomes 5 times 0.5 raised to the t over 20 power. Can you guys solve for where this equals 1? Go ahead and solve for where this equals 1. All right, anyone have an answer? Yeah, just hold it up when you have it. Yes, please. Yes. Great job. Yes, John. Yes, team 2. Good job. You guys close?
Yes.
And if you guys get stuck, remember we have Miss Wendy. You can call her over or call me over. 46 point what? Did you use intersect? Okay. Let's go over it. All right, here is the answer. What was it? 46.9? No, sorry. It's 3 decimal places. All right. So if you graph this, you should get something like this, or if you used a different window, that's fine. So second calc, intersect is number 5. Then you're going to hit enter 3 times. 1, 2, 3. Looks like 46.439. You got 46.9.
Well, I entered the graph and I even found the intersection and everything, but I got 10.744. Let me see. I don't know what happened here. Oh, I'm sorry. Oh,
Sorry, not negative. Positive 0.5. You put 0.05. You had an extra 0. All right, ladies, are there any questions on this one? Okay. Let's go on to this one. Please give me an equation to represent the situation. And it looks like we're not going to quite finish. I'm going to push your 5A homework 1 class, but start it. Yes. Yes. Good job. Yes, and yes. Good job. You got it. You guys close? Everyone got it? Awesome job. Here is the equation. Please solve for when there's 1 gram remaining. Yes, actually, it's an 8 there, I think. The decimal portion is wrong. Are you using intersect? It should be an 8. I must have written it down wrong. It's got the same thing. Yeah, then you guys must be right. I must have written it down wrong. I'll fix it. Good job. All right, the due date has been postponed. It's not right. Are you using intersect?
Yeah, we did intersect test. It's not.
Can I see? Yes.
You know how people at golf golf and they like fall off the thing?
What? I'm putting like right.
Oh, your scanner popped.
Oh yeah, I think so. It's a big day for me. I know. I'll be home before 3 o'clock. I know. Yesterday I was 14.
So it's just calculator.
All right, here is the answer. There you go. I'm going to give you a point because both times it was like just mistyping something. All right, are there any questions on this one? Okay, we'll stop here. We'll pick up on example number 3 next time. Great job today, you guys.